Okay. Okay, so first of all, let me thank Darshan to giving me this opportunity for interacting with you all. Uh, uh, and as you might have noticed, that buckling restraint braces is my area of research. I am doing research right now as a part of PhD program. So I enrolled myself for doing PhD after completing almost 2 decades of experience in the industry. Okay, so I'll tell you the quick story about that also. Okay, so just let me share the screen presentation. But before I share the screen, see, always I want the discussion in the interactive mode. Uh, and if it's a two-way communication, then and then the more knowledge transfer or the more thoughts will be exchanged. So please feel free to share any points, any questions which you find during the session. You may raise your hand. You can put it into the chat, and Darshan will facilitate for keeping those points in between. Okay, so let me share. Yeah, so I hope you can see the presentation now on the screen. Yes. So title what I have given is buckling restraint braces for retrofitting of the existing structures. Now, when we talk about buckling restraint braces, it's a very interesting concept. I think few of you might have heard about it. But I always used to say that the usage of buckling restraint braces are actually limited with our thought process. That means it can be utilized for a number of different applications or a number of different types of structures. So today, what we'll be talking about briefly in this conversation of, let's say, 1.5 hour or let's say in a 2 hours of time, we will be focusing the usage of buckling restraint braces for a retrofitting of the existing structures. But it can be applied to any new structures and to all different kind of structures. These braces can be considered. So when we say buckling restraint braces, it is nothing but it is an improvement made over the conventional bracings. So wherever we can think of conventional bracing, the application of buckling restraint braces can be thought of. Okay. So why this topic is considered, right? Because whenever I was doing the structural design for any structure, starting from, let's say, 2002, as we all know that in 2002 there was a first revision in the earthquake resistant design code. So that was an immediate reaction after the Gujarat earthquake in 2001, which was quite unfortunate event. So I just started my journey during that time only, and we started designing the structure based on the updated Indian standards. Okay. And always, whenever the Indian standard codes were updated in 2002, at that time, I hope many of you may be aware that so many draft documents were circulated for comments. And we also formed a group of like-minded engineers who were having almost, let's say, more than 40 years of experience. And somehow I was asked to coordinate that very senior group. So from that group also I learned so many things. But what we were talking as a group at that time, that it would be better, like we also focus on the execution part as well as the detailing part of the structure, instead of merely increasing the level of the design forces. Of course, there were so many documents which went to and fro, but this is the major update which we all know, that in 2001 the unfortunately the earthquake struck in Gujarat, and thereafter the revisions in the earthquake resistant design codes were taken up. So this is what we were talking, like the veteran structural engineers were having actually opinion of making Indian standard codes more simpler and opined that it is required to strengthen our detailing practices, as we just discussed before few seconds. Okay. So before we get into the subject, let's have the brief context or the brief history. Like when we talk about the usage of buckling restraint brushes for retrofitting of the existing structures from the perspective of the earthquake resistant design. So right now we will be talking in this entire talk related to the retrofitting of the structures from the earthquake resistant design perspective only. Now corrosion is another area which we will not be touching right now in this talk. Okay, so the retrofitting could be from a number of reasons, but right now we'll be focusing on the earthquake resistant design, and that's why these slide shows the quick history, like how different Indian standards were published after 2002. So 2002 was a major revision, and thereafter in 2008 steel structure code was published, and in that section number 12 was introduced for the earthquake resistant design of these steel structures. Until today there are many practical problems in that section 12. In 2013, BIS published IS 15988-2013. It is for the seismic evaluation of the existing RCC structure. And I always used to say that this is one of the most rational earthquake resistant design code, because in the preamble itself it says that whenever we are using this code, the appropriate engineering judgment must be exercised, right? And whatever is written in this code in this 15988, that is guideline. Okay. And in 2015, IS 1893 Part 4 was revised, which is for the industrial structures, as we all know. And in 2016, IS 13920 was published, as well as IS 1893 Part 1, which is the mother code of earthquake engineering or earthquake resistant design, was revised in 2017. And in 2017 again the code was published for the tall building, which is IS 16700. Okay, so this is a quick history of IS codes. Now if we get into these the code, why these codes are updating, we can see the codes are being revised, right? So this is what I believe, that now we are transferring from the force controlled approach to the displacement control approach. Now force controlled approach meaning, as we just talked, like let's say if we refer the 2002 code, for example, and there was a clause for the soft story. And what was written, that if there is a soft story in the building, then we need to enhance the design forces by a factor of 2.5 times. Okay, and now when we refer IS 1893 Part 1 2016, now same soft story is now dealt separately. What is written now, that 2.5 factor, 2.5 times amplification is removed, and instead of that now it is suggested that we should provide a shear wall, and also there are requirements of the drift control, which is identified for the different kind of other irregularities also. So the ultimate goal is that the displacement or the drift should be controlled. So this is what I believe, that now we are transferring towards the displacement control side. Now, this is also one of the important point which I'll just highlight you for your information, that the interface between this different Indian standard code is also very important, because the revision is happening in the different cycle, and that's why it is quite possible that we would have very major difference between the different Indian standard codes. Okay. Okay, so when we talk about, say, earthquake hazard in India, then I think many of you must be aware that the paleoseismology is one of the branch of geology now, which is actually focusing on the historical earthquakes that were recorded, let's say, by instruments or by other means. So actually, in this branch, we are taking the record of previous earthquake for the past 10,000 years. Uh, And also these the signatures like scarp, linear valley, mountains, sag, pond, wind gap, shifting of drainage, etc. is studied. And based on this detailed study, this earthquake hazard is then conceived, and then accordingly it is becoming the part of the codal provisions. Right. So the main purpose of this branch is to predict the earthquake hazard, and based on that, the codal provisions could be updated. So as we know that when the the earthquake strike in a Bhuj in 2001 earthquake, the peak ground acceleration was 0.55 g nearly. And the maximum or the peak ground acceleration, which is considered in our Indian standard code, is nearly 0.35 g. And as we all know that there are already warnings which were given that the moderate to very severe earthquake could be expected in the northern part of the India, right? And then that magnitude could be as high as 0.9 or up to 1 g. So the Himalaya is one of the most seismically active international region of the world, which we know. Okay, and the global tectonic plates reconstruction data also suggests that the plates are moving. So accordingly, the higher or the devastating earthquake is expected in our country in certain region, right? And accordingly, we have defined the different zones. So the current status, if we see quickly, that we have already witnessed now devastating earthquakes, in past, and may witness even higher intensity of earthquakes in the future as well. And there are so many researches are going right now when we are talking to identify the active faults, and also the microzonation is also coming up, because whenever we are talking about say non-linear time history analysis, the most basic input, which is the ground motion, that is not available with us. So for that, so many different studies are going on right now. Okay, and parallelly, see what is happening as we see in the one of the previous slide, that now Indian standard codal provisions are also gradually being aligned to the global design practices. And if we take the typical design cycle of any Indian standard, then this is in a range of 10 to 15 years. So what is happening that when the Indian standard is revised, the accumulated intelligence of the global or the other parts of the world within that 15 years is getting transferred into our codes. So with this, the Indian codes are revised sequentially for updating zones as well as for revising the design provisions. Okay. Now what happens, like, see, whenever these revisions are happening in the Indian standard codes, what happens actually? The old existing structures are becoming unsafe on paper overnight. So that's why it is required to evaluate the old existing structures with respect to the latest Indian standards for the earthquake resistant design. Okay, that's what we are going to focus right now in a today's talk. And this is what I believe, that there is a huge requirement for evaluation and retrofitting of the structures from the perspective of the earthquake resistant design. Right now, there are two kinds of structures. One is the older structures, which were designed based on the earlier codes. So definitely there could be certain kind of a deficit when we evaluate them with respect to the latest earthquake resistant design codes. And second thing, there are a number of non-engineered structures, as we know, right, in which let's say even they didn't follow the codes in totality. So this could be two broad category of the structures, in my opinion. But what I believe, that there is a huge requirement for the for this evaluation and the retrofitting. Now, when we talk about earthquake resistant design, see the design part already we discussed, that the level of forces are being enhanced in the code whenever it is getting revised. But also the detailing and execution part is very much important, right? So we need to focus on all these three verticals simultaneously. Otherwise, we are not able to achieve the required or the desired goal of the earthquake resistant design. Okay, so with this, now let's talk about the retrofitting of the existing structures. So this is the code 15988-2013, which was released in 2013, which is for the seismic evaluation and strengthening of the existing reinforced concrete buildings. Okay. Now this is very important statement which has been made, which is reach an adequate level of performance related to life safety of the occupants. That means whenever we are doing retrofitting of the particular structure, first of all we should identify what is the level of performance which is required, and accordingly we should retrofit it. So for example, if we are retrofitting let's say the hospital building, or let us say the school building, then the required level of performance would be more stringent as compared to the other buildings, right? So accordingly, first of all, that level of performance needs to be identified. Yeah, and then accordingly, the entire process, or accordingly the retrofitting mechanisms will be developed. So as we just talked that this is only guideline, but I'll just quickly give you the overview of this code, and then we will get into the buckling restraint brace. But before that, it is better to understand the overall approach which is mentioned in this code, like how step-by-step approach is given before finalizing the mechanism for the retrofitting. So the seismic performance of existing buildings is evaluated now in relation to the performance criteria in use for the new buildings, right? So whenever we are approaching for the retrofitting of any existing building, then the criteria will be same as of the new buildings, and that's what is more challenging, right? Because let's say the new buildings are designed with respect to the older provisions, older codal provisions. So that's why this is one of the important part which is mentioned here. So we'll get into the subsequent slide, but modification to seismic forces as given in IS 1893 and to material strengths will be applicable to both preliminary and detailed assessments described. So what is happening? There is a factor introduced which is a lateral load modification factor for the reduced usable life. So for example, let us say if I am doing retrofitting for a 30-year-old building, then in that case, the residual life of the structure is, let's say, for example, 20-25 years, for example. So in that case, there is a provision we can reduce the lateral load because the service life of the structure is now reduced. And of course, in no case this factor should be less than 0.7, but there are factors and formulas given in the code for this. So this is a good one of the good approach by which we can reduce the earthquake force. And of course, whenever we are doing the retrofitting, whenever we get the retrofitting assignment, this is a common problem that we do not have access to all drawings, all design calculations, etc. So in that case, the value is given here, like which is a knowledge factor. So we need to divide our earthquake force by this knowledge factors. So if I have very little knowledge, then my earthquake force will become double because it will be divided by 0.5. And if all details are available, then this is 1. And we can see there are intermediate factors are also highlighted in the code, so which is known as the knowledge factor. So two important factor, one is the lateral load modification factor and another is the knowledge factor. Okay, and the first step is to carry out the preliminary evaluation of buildings. Yeah, and this will involve the broad assessment of its physical condition, robustness, structural integrity, and strength of structure, including simple calculations. And it is defined very nicely in the code. So if you're interested, you can refer to the code. And even for the site visit also, there is a very detailed list which is given, like what exactly we have to check on the site. For example, building type and site soil classification, geological site hazards, spatial construction anomalies, and then each head, whatever I'm showing right now, is detailed out in the code, but it's a very elaborated checklist for the site visit. So the first step is to do the preliminary evaluation, and preliminary evaluation is again divided in two parts. One is the configuration related checks, and another is the strength related checks. So configuration related checks are again categorized in load path, redundancy, geometry, weak story, soft story, vertical discontinuity, mass, torsion, adjacent buildings, short columns, etc. And strength related checks like shear stress in reinforced concrete frame columns, shear stress in shear walls, axial stress in moment frames. Now these everything need to be derived based on the simple manual calculations, because it's a preliminary evaluation first we are doing. And thereafter, these are the checkpoints which are mentioned, that, like, let's say if it fails to comply with the requirements of the preliminary evaluation, or let's say if it is 6 stories or higher, if it is supported on liquefiable soil, or if it is located near active faults less than 15 kilometer, or let's say if there are inadequate connections. Now, inadequate connections meaning let's say if reinforcement detailing is not as per the IS 13920. So in short, let us say if ductile detailing is not followed. So these are the different checks which are given, and based on that, it is recommended that the building should go under detailed evaluation. Now, in the detailed evaluation, of course, the condition of the building components like deterioration of concrete cracks in boundary columns, masonry units, masonry joints, etc. On-site non-destructive testing will be done. Laboratory analysis of samples will be done, okay, in the detail. Now these are the two factors which we just discussed, which is a knowledge factor, and another is the lateral load reduction factor, okay, which will be applying while calculating in the preliminary stage as well as in the detailed stage. Okay, I'll just showcase this also. Like, this is the stiffness modifier which were introduced in this code for the first time in 2013. Of course, it has not got such limelight like other codes, but I just want to highlight that this was published in 2013. Okay, so after performing everything, the acceptability criteria is that all critical lateral force resisting elements have strength greater than the computed actions, and RIP checks are satisfied. That means if everything is satisfied, and if ductility and detailing of structural members are adequate, then no retrofitting is required. But let's say if few elements are not meeting the above mentioned requirements, so in that case, the again further analysis is suggested, which is a non-linear analysis, which is, let us say, the pushover analysis, and by which we should demonstrate that whether these elements are causing kinds of stability loss, or let's say could it initiate the progressive collapse, etc. And if answer is yes, then definitely these elements shall be retrofitted. And after completing this process in detail, which we have discussed in very brief, the finally will come down to the seismic strengthening options and strategies. So our overall aim for doing seismic strengthening is to increase the redundancy of lateral load resisting elements to avoid collapse and overall stability, right, as we all know. So now, what could be the kind of retrofitting mechanism? The strengthening could be at a member level, eliminating or reducing structural irregularities is also one of the option. Then strengthening at a structural level, and let's say supplemental damping, that is the addition of damping or isolation, jacketing, addition of reinforced concrete shear walls. Okay, so there are a number of options which are given in the code. Okay. So as we discussed, that there are numerous buildings which actually require retrofitting, because one of the major reason, as we discussed, that Indian standard codes are updated gradually. So the structures which are designed before, let's say, before the latest Indian standard are becoming unsafe on the paper. Now, how to retrofit them? Of course, we have seen the few methodology which are suggested in the code, but all methodologies are quite cumbersome. And let's say, for example, if I'm adding shear wall in the building, what happens actually? My building is becoming more stiffer. And because of that, it is going to attract higher seismic force, right? And the displacement or the drift, whatever we'll be getting, that will be too less because structure is not flexible. And the same is the problem with the conventional brace. So now let us explore these buckling restraint braces, how it, what is actually the buckling restraint braces, what are its different usages. Let's see some theory also of the braces, how it was derived. So if we talk about quick review of the existing structural systems for these structures, so we can divide the structural system in two categories. One is the, let's say, the conventional braces, which we are providing in a steel structures, or the moment resisting frame for the steel structures. Okay. And for RCC structure, if we talk about, then it is a moment resisting frame or shear wall or dual system for RCC structures. Now, problem with this system, as we just discussed, that these systems are used in isolation or in combination, right, as per requirements. Now, moment resisting frame alone is too flexible to meet the stringent drift criteria as per the functional requirements. Okay. And of course, performance of the structures using conventional brace is better than the exclusive moment resisting frame. So always there is a preference of putting conventional brace in the structure with as compared to the MRF, but always because of the stringent functional requirement, let's say we might have to go with the MRF, but conventional brace is always a better option. But what is the problem in the conventional brace? That they have very good yielding capacity in the tension force. But what happens if we talk about earthquake force? So that is going to be the reversal cycle, right? So in the reverse cycle, the same brace will have to resist the compression force. Now, as you all know that for the steel brace, there is a substantial difference in the capacity when we talk about the axial tension capacity of conventional brace and axial compression capacity of the conventional brace. And capacity of the axial brace or the axial compression capacity of the brace is very less because they are prone to buckling during a compression, right? So conventional brace will reach maximum strength at very small drifts, and the capacity will be degraded substantially after buckling in compression during the larger deformations. So what is happening? See, this is the basic problem in our design, and this is what uh, I was thinking across since last 10 to 15 years, that what could be the solution. Because see what problem happens now, my conventional brace, whenever I'm putting into the structure, it will fail in compression. Okay, so to avoid this compression buckling, we will have to increase the size of the conventional brace. So what will happen? My structure will become more rigid, and since my structure is more rigid, it will again attract higher earthquake force. And because of that, the sizes of the braces are also quite impractical. I'm talking about very heavy industrial structures, or let's say very tall structures, and hence there is a requirement of certain system which is intermediate of this our max moment resisting frame or the conventional brace. and whose strength, let's say, doesn't decrease after yielding. So this is what I was just sharing, that while working with oil and gas industry, thermal power industry, always these thoughts was generating in my mind, that there has to be certain different kind of a system which we need to think of instead of this conventional systems. Now, fortunately, while attending one of the workshop of from the Japan Society of Seismic Isolation, I just came across this concept of buckling restraint brace. So it is nothing but when we say buckling restraint brace, the concept is very simple, that we want to get the similar capacity of the conventional brace in axial tension and the compression. That means whatever capacity it has in the axial tension, the similar capacity it should exhibit in the compression also. So this is the concept, okay. And the whole invention of this BRB occurred because of this limitation of conventional brace only. Okay. So now what we see on the screen is a BRB, buckling restraint brace. A short form is BRB. So as you can see on the screen, it is also looking like as a conventional brace in appearance. Okay. And it is designed to allow the building to withstand cyclic lateral loadings, typically earthquake induced loading, and its cross sectional area can be significantly lower than that of the rectangular regular braces. Because their performance is not limited by buckling. So what does it mean? That the size or the stiffness of this BRB is very less as compared to the conventional brace. Okay, so we'll come to this part, but because of these lesser stiffness, the structure is becoming more flexible, and because of that, the earthquake force on the structure actually reduces, and that's what the prime advantage will be with us whenever we are approaching retrofitting of the older structures, because we, let's say, by providing certain elements, if my structure is becoming more rigid, then again it will start attracting higher amount of the earthquake force. So that's where this process will be very handy in application. Okay, so quickly let us say then what is BRB and what is the history of BRB. So now, firstly, it is not at all a new technology. It was being developed, or rather it was conceived in early 1970s of time. And when I was actually referring to the history of this BRB, the first research was done in Japan and India. And of course, thereafter, the research continued in Japan. And we didn't do much research on that. Of course, Mr. Sridhar from India also developed a tube kind of a BRB. But till if we see as of today, there is uh, no application in the real-time projects when we talk about BRB across the country, because one of the reason is that still it is not included in the Indian standards. Okay. So in 1970s, the basic concepts were developed, and of course the whatever different models they created, those models were having the same working principle, or rather the thought process was very simple, that they wanted to achieve similar capacity of the brace in the compression as well as in the tension. Now, in 1970s, of course, there were a number of failures. There are a number of different configuration they tested, different methodology they tested, and finally the BRB prototype uh, was almost ready then, and the first application was done in 1989, where it was applied in a 15-story steel frame. And thereafter it got quite popular and used in almost 160 buildings in Japan. And if we talk about the inclusion in the codal provisions, then Architectural Institute of Japan, AIG, firstly included this BRBs in their design guideline in 1996. And in US, first time it was introduced around 1998, as per my understanding. And thereafter, this BRB has become popular in all different countries, and numerous researches are going on in Japan, USA, China, Taiwan, Canada, Iran, New Zealand, etc. And in 2005, BRB was introduced in AISC 341 2005, which was again revised in 2010 and 2016. So let me tell you, still as of today, still there are a number of researches happening on a BRB, and there are numerous type of BRB. We will see in a subsequent slide, which are being developed by local region as per the availability of the materials and based on the ease of the fabrication, etc. So this technology is not very new. It's almost in existence since last 30 years, but we are not using it at a national level. So, and numerous studies were done on BRB across the globe for areas like low cycle fatigue, control of residual drift in BRB, connection buckling, local buckling, and still the research is going on. And major international standards recommended full-scale testing of the system to ascertain the intended behavior of the BRBs during the seismic event, meaning all major international standards as of today, they recommend that BRB has to be tested full scale, because BRB is a manufactured item. So it's a kind of it will be developed by the particular manufacturer, and then at the premise of the manufacturer, the full scale testing of this brace has to be done before it is getting implemented at a project level. And there are guidelines given in the different international standards. Of course, those guidelines vary from standard to standard, but from those guidelines, the testing should be carried out considering those guidelines. Then it can be used in the real projects. Okay, so this let's now get a little bit more into the BRB. So what are the main components of BRB? Now, there are different types of BRB. We will touch upon only one or two maximum. If you're interested, you can contact me, and then I'll share across many details related to this. But the most popular BRB is the unbonded brace. Why it is called unbonded brace, we will see in a subsequent slide. But the most important part is the steel core, which is the main component resisting the axial load, which is known as the steel core. And then there is a restrainer, which is for preventing the buckling. We will see each part in the subsequent slide along with the figure. So right now you can just remember the name. One is the steel core, another is the restrainer, which will prevent the buckling, and another is the debonding material or gap, which is very, very vital and the most important part for ensuring the Poisson's ratio effect in the steel core. So for allowing the expansion and the contraction of steel core, which is independent of the restrainer. And then finally the steel core will be connected to the gusset plate through the transition piece, which is non-yielding and also known as a neck, since there is a possibility of rotation or global buckling of BRB at the neck location. So now let us try to see the steel core, restrainer, debonding material gap, etc. in the figure. Okay, so now what we see on the screen is the L section, longitudinal section, elevation, and the cross sections of BRB. So first, let us see this section AA, and in section AA we can see that there is a steel core. So it is nothing but a steel plate, right? I hope you can see the steel plate. Uh, and this is the steel plate which will carry the compression as well as the tension. Now surrounding to these steel plate, we can see that there is a concrete filling, or let's say the high strength mortar which is being filled. Okay. And to keep this mortar in position, there is a steel tube. Okay, so this steel tube which is on the outer side is called a restrainer, and the plate which we have in the central portion, that is our steel core. And here on these steel plate, between this steel plate and between this high strength mortar, there will be debonding agent and the expansion material. Now, why this debonding agent is applied here? To allow the free movement of this plate. So the whole purpose of these concrete fill is is to prevent the failure of this steel core in the higher buckling mode. Okay, right. So here we can see this is the yielding region. The in between portion is the yielding region. Then this is the transition region, and finally this is the connection. Okay. And here we can see these are the different types of the core plate. So here we can see the core plate is having rectangular section. This is two rectangular placed in this way. This is restrainer is varied in a restrainer is having a circular shape, and in all these three figure we can see the white color border line with this black color steel core. So that white color is nothing but it's a debonding gap. And now when we calculate actually the debonding gap, then that debonding gap we get in a magnitude uh, of 1 mm to 2 mm. And that's why very high and stringent fabrication control is required for the BRB. And that's why the full scale testing is suggested, because quality control, fabrication control very is required to a great extent when we talk about BRB. And a couple of other types of BRB we can see is where we can see the types of restrainer. These two are steel, completely steel BRB. So this is a one steel section, circular steel section, and in that steel section one more steel tube is inserted. So the steel core is of a circular type, and here we can see this the steel core is placed in these steel members. Okay, so the concept is very simple, that we want to get a similar kind of a strength in compression and in the tension. So with this we can see that the stiffness of this steel plate will be very less as compared to the conventional brace, because the conventional brace will not be restrained against buckling, but here the steel core which is taking the axial force is restrained from the not restrained from the buckling, but it is restrained from getting buckled into the higher mode shapes. Okay, and that's why we get almost a similar capacity in the compression and the tension. And here we can see that we could have n number of different possibilities of BRBs. So these are a few types of BRB. Like now there are several manufacturers who export internationally, as well as there are unique BRBs which are being developed locally also. So it may be uh, distinguished based on this restrainer shape, what we just saw in the previous slide, that restrainer could be square, rectangular, circular. Uh, and also there is a core material. Now see, when we talk about the steel core plate, there I think there is some disturbance. Uh, yeah, it's okay now. So the core material, like when we were talking about the steel core, now this material can be of low yield steel. Now, why it is low yield steel? Because let's say in the effect of the extreme earthquake force, always we would wish that the first element which should buckle, that has to be buckling restrained brace, or that has to be this core material. Now if this material, core material, is having relatively very high yield strength, then the columns and beams of the structure could buckle earlier than this BRB. That's why generally low yield steel is preferred in a steel core section. And the debonding material is also varied from manufacturer to manufacturer. I have mentioned a few names here: silicone, rubber, craft, tape, etc. But this again varies from manufacturer to manufacturer. And as I told you, debonding material is very important. So if let's say if there is no debonding between the core and the concrete, or let's say the high strength mortar, then what will happen? The axial force from the brace will be transferred to this concrete high strength mortar, and that high strength mortar will crack actually. And that will lead to the failure of the brace or prematurely. Okay, and that's why debonding material gap is very important. Now let's say in another case, debonding material gap is increased from, let's say, 1.5 mm to it has increased to 3 mm, for example. So in that case, the capacity of the steel core will be reduced substantially. So that's why the strict fabrication control is required with respect to debonding material. Now the core shape also could be of different type, like rectangular, cruciform, etc. What we saw in the previous slide. The connection type is also varying. Like, see here we saw that the connection is bolted, right? But there are several different types of connections: bolted, pinned, and welded, which are again developed by different manufacturers. And also there is a all steel BRB. So in all steel BRB, these two can be considered as a all steel BRB, in which there is no concrete, there is no high strength mortar. So these are few types of BRB, and again in one type we could have subtypes of BRB, right? So this we just touched upon, like what is the importance of the debonding gap. The restrainer is the hollow section, generally filled up with the mortar to prevent buckling of steel core in the initial modes. Okay, and the buckling of steel core in the initial mode is prevented, and the debonding gap is decided in such a way that the steel core can expand and contract freely to have almost similar capacity in tension and compression. And with this philosophy, the debonding gap is resulting in range of, let's say, 1 mm to 3 mm. So the higher debonding gap than designed gap would result in the lesser compressive capacity as compared to the tensile force. Hence the strict, very strict fabrication control is required while manufacturing BRB. And after strict manufacturing control, again full scale testing is required to validate and to see whether the intended performance we are getting from the BRBs or not. Okay, so these are the first of its application. Like what we can see on the screen is a Nippon Steel headquarter in Tokyo. And this is what the BRB experiments which were done in 1987. And this is the typical BRB installation. Okay. And just one more part here, when we were looking into this figure, the connection region is very important, like what we were talking about, a neck region. Because let us see here in the central portion, there is a steel core and there is a restrainer and then there is a concrete fill. So this portion is, let us say, we have taken care, considering the strict fabrication control, putting the appropriate debonding gap, putting appropriate steel core. But here we can see that again this steel core has to be connected here. So there is going to be this transition region, and after this transition region there is a connection region. So we will see in a subsequent slides a few photographs like how this connection is very much important, because this portion is relatively rigid, and there is a possibility of rotation of the member at this point if it is not detailed adequately. Okay. So here we can see again it's a full scale testing which was done in 1987, and still till today still full scale testings are required for the BRB. Right, and this is a typical figure which it shows the BRB installation. Okay. So what is the overall design philosophy for the BRB? These following shows uh, the step by step or the salient points which we must consider when designing the BRB. First of all, the restrainer doesn't allow first mode flexural buckling of core. Now, what does it mean? The restrainer, let's read out again. Restrainer doesn't allow first mode flexural buckling of core. So let us say, for example, we are talking about a rectangular steel plate. So what is going to be the first mode of the flexural buckling? It's nothing but by Euler formula we can calculate, which is pi square EI by L square. Okay, so from that we can work out what is the critical force which would trigger the buckling. So the most important role of the restrainer that it has to restrain the uh, the the buckling of the steel core plate in the first mode, which is a first flexural buckling mode, right? Second thing, the debonding mechanism to allow for Poisson's effect of steel core. So the debonding mechanism must allow for the Poisson's effect, meaning the steel core should be free for expansion as well as for the contraction while application of the force. So even if we are putting high strength mortar into this BRB, there is not going to be any positive connection between this debonding gap. And also there is very interesting story which I was finding, like from where this debonding gap has come into picture. Like when this BRB was being invented in 1970s or 1975, so they were not getting much amount of success as per their conceptual thinking, because earlier they were not providing any debonding gap. So what was happening, the entire force was getting transferred to the concrete only, even if that steel core was applied. So thereafter, after doing number of experiments, they came with this approach of debonding mechanism so that the steel core is free for expansion as well as the contraction. So if we study, if we get into the more detail of BRB, what will happen that during the contraction, or let's say, first of all, let us say the during expansion, for example, let us say if my BRB is coming in the tension, so in the first instance the steel core will be elongated. So because of that, the cross sectional area or or let's say the depth of that section will reduce because it is being elongated, it is being stretched. Okay. And in the second reversal cycle, when the force will come on this member, at that time during contraction the thickness will increase, right? and and accordingly the step by step the methodology was prepared, was mathematically calculated, numerous experiments were done, and based on that this debonding mechanism principle came into a picture. But it's very important to have debonding mechanism to allow for Poisson's effect of steel core. And as we have discussed couple of times in the earlier slide, like if debonding mechanism is, for example, let us say is not available in the BRB because of XYZ reason, then the whole purpose of this BRB wouldn't be achieved. That means the capacity of this BRB in the pure axial tension and the compression won't be similar. Now, higher mode of buckling of steel core should not result into bulging of the restrainer wall. So let's come to this first point again, that the restrainer is not allowing first mode flexural buckling of the core, okay, but it will allow for the higher mode of buckling of the steel core, right, which is, let's say, the mode number 3, mode number 4, or mode number 5. And now that mode number will dependent actually upon the debonding gap which we have provided. So whenever the higher mode of buckling of steel core will occur, let us imagine that now the load is being applied to continuously on the brace. So first tension compression, tension compression. So what will happen? The force will increase on the steel core, and uh, and in the subsequent cycles, when the force is getting increased, there is a tendency of this steel core to buckle in the higher mode shapes. Okay. And whenever there will be buckling in the higher mode shapes, what will happen? This steel core will transfer the thrust to the adjoining motor. And at that time there is going to be the thrust which will be produced on the restrainer wall. So that's what is the basic criteria which we are talking about, that higher mode of buckling of steel core should not result into bulging of the restrainer wall. So for that, the restrainer wall or the restrainer member thickness shall be sufficient, or it should be at least having capacity of carrying an axial load of 1.5 times higher than the steel core capacity, so that the restrainer should not become a weak link. One more point is the global out of plane stability to be ensured, including connections. So as we were discussing in the previous slide, now when we talk about the BRB, the central portion is rigid, but at the connection level, uh, there will be a neck portion which we will see in a couple of slides. So if this stability is not ensured, then naturally the capacity of BRB is very less, right, as compared to the theoretical calculation. One more thing, low cycle fatigue capacity should be sufficient for the expected demand. So what happens during seismic events? See, let's say for once the earthquake has struck, now there is a possibility of getting an aftershocks on the structure, as well as, let's say, if my BRB has taken up one earthquake cycle. Now, how many more earthquake cycle it could take, or is it required to replace my BRB after say, let's say, the earthquake cycle? So whenever earthquake is striking to the structure and let us say BRB is applied, then definitely BRB needs to be inspected, and if required we should replace the BRB. So that is the low cycle fatigue capacity also should be sufficient, so that that replacement doesn't warranted for majority of BRB. Now here one interesting thing, like how to see the damage in the BRB, because we have the restrainer wall. Within the restrainer wall there is a concrete, and within a concrete there is a steel core with the debonding gap. So there was one more idea which was suggested, that it would be a good practice to install CCTV camera within the BRB in the concrete, so that we can see that whether the high strength mortar or the concrete fill, whatever we have done, is intact or is it been damaged. So if it is damaged, then we need to replace the BRB. So that is one of the solution, which was suggested, just for checking the adequacy of the BRB after withstanding a cycle of the earthquake force. So in short, when we talk about design philosophy of BRB, we can put it in a simple words that no other parts in a buckling restrained braces should become a weak link other than the steel core, so that the fullest capacity of the steel core can be utilized in the axial compression as well as in the axial tension. Okay. So if we talk about the restrainer design criteria, so it was established in 1988 through experiments and based on the equation that restrainer buckling capacity in order of 1.5 times greater than that of the yield strength of the core member is enough for the initial deflection of 1/200 for L upon D is equal to 32.9 to avoid local buckling in the restrainer, or thickness of restrainer plays very important role. So what it says essentially that whatever capacity of steel core is there, then the restrainer buckling capacity should be at least 1.5 times higher. The restrainer buckling capacity should be 1.5 times higher than the yield strength of the core member. Okay, so this is what was established through the number of studies in 1988. And as we discussed that the thickness of restrainer plays very important role for defining the buckling capacity of the restrainer. Okay. One more experiment was done. Of course, there are numerous experiments. I have just highlighted a couple of them here for the quick understanding. So numerous experiments were performed and found that restrainer specimen having diameter to thickness ratio 65 buckled locally, and the specimens having diameter to thickness ratio of 25 did not buckle. So this is one more study which was done for identifying what should be diameter to thickness ratio. Okay, and when that ratio was kept around 25, then there was no buckling. Okay, so here we can see the local bulging and the out of plane bulging of the restrainer. So this is one of the most important criteria of BRB as we are talking. So here we can see the full scale testing of BRB is in progress, and this portion which is highlighted and then it's blown off. If we see as a cross section, what is happening here inside within the BRB. See, this is the steel core, which is in the white color. Okay, and this steel core as get into the higher buckling mode shapes, and because of that it is now exerting the forces on the restrainer wall. And here we can see that the restrainer wall has given up. So this is one of the design criteria for BRB, that restrainer wall should be stronger enough so that they did not bulge outside before achieving the full yield capacity of the steel core. And here this is out of plane local bulging failure. So again, in the cross section, it is shown here that the steel core has bent, and then it has exerted the pressure on the restrainer wall, and we can see that there is an bulging in the restrainer wall. So in short, the restrainer has failed. So in both the cases, we need to increase the thickness of the restrainer. Okay. Okay, the connections are very important part. Like whenever we are talking about the connections, at least for BRB, this is one of the most important part, because the sleep at connections has to be prevented to ensure the symmetrical hysteresis. That is first part. And generally two types of connections are adopted. Either they are bolted connections using high strength friction grip bolts HSFG, or two pinned connection. So these are several experiments done. Only I have highlighted only few of them. There are numerous experiments on connections. So in one of the studies, stiffeners were added during testing of full scale of BRB, which prevented out of plane buckling of the gusset connections with the beam column. Like whenever the BRB is added, let's say for example, if it is added on the beam, then that beam also needs to be strengthened in a lateral direction at wherever the BRB is joined. Otherwise, the performance of BRB is affected quite adversely. Now, in one more study, the stiffness requirements for the connections as well as of the girders to prevent out of plane buckling of BRB to achieve its full strength was conducted. And again, in this all different study, the junction detailing requirements were identified. And in this study, performed large scale shake table test for BRB placed in a chevron arrangement, and BRB is having transition segment embedded in the restrainer by 1.5 times. We were looking to the transitions piece right now. Okay, in the few previous slides. So here, even that the embedment of the transition piece was also varied. Let's say from 1.5 times the depth of yielding section, and then the overall performance of the BRB uh, was evaluated. Okay, here's it was studied and proposed restrainer moment transfer capacity for different types of connections, and the same were checked with the full scale BRB test. So there are numerous work which has been done, theoretical, mathematical, and then the full scale testing is done to validate it. And then wherever there are gap areas, again the theories are being updated. Okay, so this is the connection we can see during testing. So if we talk about AIJ, so there is a recommendations to provide rigorous evaluation methods for BRB connections for out of plane buckling. Okay. So here we can see in this figure, this is the restrainer portion. Okay, then there is a transition and then there is a connection. And here we can see while application of this axial force, this connection has given away and there is a buckling or the rotation of the BRB at this point. So it means that the BRB has failed and now it cannot take any force, obviously. So there are very detailed approaches given in the AIJ as well as the book which is prepared by Takeuchi. So this is the cantilever gusset, or this is the restrainer and continuity. So again, there could be a different concept, like in this first concept, it's a cantilevered gusset, meaning fixed at this point and then it is a pinned at this point. Okay, so it's a fixed at this point and pinned at this point. And since there is a zero moment rotation capacity, we can see that entire beam, entire this portion of BRB is being rotated. Whereas in this case, we can see that the transition piece is embedded into the restrainer for a certain time, or rather for a certain length. So in that case, we can see it's a continuity of this plate. It's not becoming pure cantilever. So it's a restrainer and continuity, and both type of a BRB will have a different behavior when it comes to the out of plane buckling. So accordingly, detailed methodologies are given in the different standards as well as in the book. And here we can see this is the moment transfer capacity is lost at the end of the restrainer. And this is the gusset plate which is transferring the bending moment. So naturally, the capacity of BRB will be very less in this type 1 approach as compared to the type 2 approach. So that's why this restrainer and continuity is very important. Yeah, this is one more example like where BRB is tested, and what we can see is the importance of connection design again. So on the first figure, we can see that the BRB is being tested and it has failed at this point at this connection, like it's a kind of a cantilever connection, what we were just looking in the previous slide, wherein this BRB has rotated. So now to make this connection adequate, again, these plates are added here. So here we can see there are no stiffeners on this plate. So now these stiffeners are added, and thereafter further experiments were done. And here we can see that now the specimen is intact. So the philosophy of design is very simple, that no other parts of BRB should fail before the steel core reaches its yield strength. Okay, and accordingly all different parts are to be designed, as well as full scale testing has to be carried out to check the performance of all different elements during the cyclic loads. So the unique advantages of BRB as compared to the conventional press, if we have to note it down. First of all, BRBs have symmetrical hysteresis. Why symmetrical? Because it has almost similar capacity in axial compression and tension. In fact, now if we take actual statistics of the capacity, then the capacity in the axial compression is actually 10% higher than the axial tensile capacity. So why it is coming 10% higher? Because whatever amount of debonding material or debonding gap which will provide, there is a possibility of low friction between the debonding material and the mortar, and because of that the actual compression capacity of BRB is, let's say, almost 10% higher than the actual tension capacity. Okay, and that's what is written here, like due to this low friction, certain amount of compressive force is transferred to the restrainer, resulting in the higher compressive strength than the tensile strength. Okay, The another most important advantage of BRB is that they yield at the very lower drifts. That is, they yield before the main structural frame, so they can also act as a kind of a fuse, we can say. So these are the first element which will act during the earthquake event, so that the main structural frame can remain intact, or rather in other words we can say that the main structural frame will be in the elastic range. Hence, in the overall design philosophy of seismic design of structures, it can be ensured that the BRBs will yield and the main frame will remain elastic. So, of course, few iterations to be made on this, and then accordingly it can be done. Now, as we discussed that the BRBs are very slender in terms of the cross section, in terms of the stiffness as compared to the conventional braces. So it is possible that we may get higher drifts in the structure. And as we were discussing in the initial part of the talk, that the drift control is very much important. So there has to be could be trial and error in the design philosophy, or in the design cycle. Let's say in the one trial I'm getting the drifts value which are higher than the functional requirements, or let's say it is exceeding beyond the codal provisions. Then we will increase the stiffness or the size of the core plate or the size of a BRB till we uh, achieve the required performance criteria. And also we will keep a check on the structures, remaining structures, that it remains elastic in our analytical model whenever we apply the earthquake force. Okay. Further unique advantages of BRBs as compared to conventional braces are the another most distinctive advantage of BRB as against the conventional brace is that the stiffness of BRB can be adjusted. Just now we talked about it, that the stiffness of BRB can be adjusted in such a way that all stories of the structure will yield simultaneously. Now this kind of adjustment is not feasible in the conventional braces. Then finally, use of BRBs in the structure will increase the ductility. As we have discussed, the structure will become more flexible, and because of that the time period of the structure will increase, and hence there is a reduction in the seismic base shear, and because of that it will result into the overall economy with respect to the conventional brace. These are few pictures of BRB installations. So we can see in this first figure, this is the restrainer. Then there is a steel core mortar which is not seen from the outside, and then this is finally the connection part which will be connected to the gusset plates. Okay. So this is one type of BRB. Now here this is another type of BRB where we can see it's a completely pinned connection, only single bolt connection kind of connection here. Okay. Yeah. This is again a different type of BRB. I think this looks probably the welded connection, and this is one more type of BRB here. The concept is similar here, but I think we can see the cruciform section here. I think here also there are cruciform section. But this manufacturing or the types and detailing of BRB varies from the manufacturer to manufacturer based on their own in-house research and the enhancement in the knowledge. Okay. Okay, this is a very important area, that whenever we want to go ahead with the BRB, then the interface between design engineer and the BRB manufacturer is very, very important. Because as we talked that it is a manufactured item, and at the same time it affects the overall behavior of the structure. So there has to be very detailed interaction between the structural design engineer and the BRB manufacturer. So what will happen? See, first instance, structural engineer will create the let's say the structural model using first order elastic analysis. At least he will find out that what are the forces which are there in the structure, and then based on that, how much stiffness is required. Now, based on the, certain data, based on those data, BRB manufacturer will furnish the appropriate BRB data, which will be again put into the structure, and then again the performance of the structure would be seen, and that this way to and fro will happen for several times till the results are received in the required tolerance. But a very great amount of interface is required between the design engineer and the BRB manufacturer whenever it is being implemented in the real projects. Now, this BRB can be used differently. These are a couple of ways. Here we can see these are the BRB. This all are BRBs. And these all other are gravity frames. So the entire lateral earthquake force will be taken care by this BRB in this frame. Okay. So here what is done essentially, this one frame could be of BRB, second frame is of gravity frame, and third frame could be let's say the having moment frame, which is MRF. Okay. So accordingly, we can have a mix type of a structural system based on the amount of loading and based on the extent of the structure. There's also one more example, BRBF with elastic truss. Okay, so this is nothing but elastic truss, and this is the BRB. So BRB will work as a fuse element in this case. Okay, in this second figure. Okay. Now there could be one more application which is a schematic BRB configuration, and here the column itself is considered as a buckling restraint brace. So as we just discussed that the element is very strong in the compression, it is having almost similar strength as equal to the tension force. So accordingly, this is also one of the concept derived that we can use this buckling restraint brace in the lower stories wherever the compression forces are very high, so that we can achieve the intended results. So that's why I just told you that whenever it comes to the usage of BRB, in fact, it is a limitation of our own thought processes. It could be used at a number of places, or wherever we can think of. The BRBs can be used in the RCC structures also. And the most important part for this BRB will be like if we are providing this BRB, then it's going to be a single strut in a particular story. We need not provide the cross bracing here, because the each individual brace is capable of taking the equal amount of tension and compression force. So irrespective of the direction of earthquake force, the brace would be able to take care the applied loads, and that's why it is creating ease of installation. So now let's say, for example, if we want to retrofit one of the existing RCC building, then this is the probable way by which we can do it. We can add the braces in this pattern instead of adding a complete shear wall, which will require so much demolition, which will require so much other modifications in the structures. Instead of that, we can provide BRB in this pattern. This is the typical connection detail. Of course, connection has to be done very thoroughly to be checked at the site. Constructability is very important, but this is one of the way shown here. But with these, what happens that the structure becomes more flexible relatively as compared to the if we would have provided the shear wall here, and that's why it comes as a handy option in my opinion. Whenever we require to provide shear wall, then I think this brace could be installed relatively very easily as compared to the providing shear wall in the existing building. Okay, so what is the way forward for this BRB? So there is a potential of using this BRB technology for retrofitting of the existing structures, and also not only for the retrofitting. Right now our focus was on retrofitting, that's why we limited our perspective only to the retrofitting, but it can be used for any kind of a structure, for any kind of an application. Okay, it's just only limitation of our own thought process. The significant amount of interface is required between engineer and BRB manufacturer while the design process. Strict quality control is required for ensuring the intended performance of BRB. And it is very much important that BRB is included in Indian standard codes for ensuring the standardization and quality assurance. So before it is getting implemented in the real projects, I strongly believe that it should be included in the Indian standard codes so that we can achieve the standardization as well as the quality assurance can be achieved. Okay. Okay, these are the few references which from which I have taken the material. Okay, so this is all from my side. Now, if you have any questions, I'll be glad to answer on this topic. Yeah, so over to you, Darshan.
Yes, sir. Any questions from participants?
Yeah, anything, any questions, anything else, if you want to would like to share, may raise your hand or put it in the chat box.
Sir, it is Urvesh here. I just very much